Electricity, 3 charge problems. Questions to ponder. How do you calculate electric force, field, and potential with 3 charges? And what do the force and electric field vectors look like when added together? So for our force problem here, we have this illustration, and our job is to find the force on this charge 3 right here. And so we have the value of that charge, but we want to find the force acting on this charge that's provided by these other 2 charges, Q1 and Q2 here. We want to draw the component force vectors and total force vector that's acting on Q3 here. The other things that are given besides the 3 different charges is their polarities and also the sides of the triangle. So here is our illustration again, and the first thing we need to realize is if we're referencing Q3 here, Q3 is positive, so the force on Q3 that comes from this charge of positive 50 microcoulombs from Q1, since these are both positive, they're going to repel, plus the electric field from Q1 is going to be going outward here. So the electric force is going outward here. So F1 is what I'm calling the force on Q3 created by Q1, and that force vector would be going upward in this direction. Next, you can see that Q2 is negative, so opposites attract, and we'd have an attractive force vector from Q3 pointing back toward Q2. So we can do a quick sketch of those 2 force vectors. At this time we wouldn't know their relative sizes, but we can at least know their directions to start with. And we can actually calculate the amount of these 2 forces at this point in time. That would be really the next step, is to find force 1 here. Again, I'm calling that force 1 the force of Q1 on Q3. So we use Coulomb's law here, K Q1 Q3 over R squared. And so we have our, and to simplify things, I didn't put units in all of this because the exponential notation's messy enough. So anyway, we have our constant 9 times 10 to the 9th times the 50 micro coulombs, so that's times 10 to the negative 6, times the 4 nanocoulomb charge on Q3, so 4 times 10 to the negative 9 for nano. And then that's divided by the 0.3 meters squared. So we converted this 30 centimeters into 0.3 meters in this Coulomb's law equation. And after multiplying all that and dividing by the square of 0.3, we get 0.02 newtons. So this force is 0.02 newtons long. We'll do the same thing now, but we'll find F2 here. So F2, using Coulomb's law, is the force on charge 3 that is created by charge 2 here. So using Coulomb's law and plugging in all of our numbers, now our distance between them is 60 centimeters, or 0.6 meters squared. And we get 0.005 newtons for F2. And once we have those 2 forces, now we have to do vector addition of these 2 forces together to find out what our overall force is here. So to find out the overall force, we have to break these 2 forces into their horizontal and vertical components. So F1, that's an easy one because we can see that it is completely vertical. There's no horizontal component. So there would be 0 horizontal force, and all of F1 is in the vertical direction. So that one's easy. And usually that's the case. We'll usually give you one of those vectors in the vector addition as an easy one. The next, now we have to break F2 into its 2 components. So the horizontal component of force 2 would be F2 times the cosine of theta. But I guess before we do that, we have to know what theta is. And so theta right here for this would be a negative angle. And so how do we find that? Oh, I see. That's kind of an opposite interior angle here. And being an opposite interior angle, we can, if we find out what this angle is, is really the same angle up here. So I really need to find out what this angle theta is down here. To do that, I'm going to use the structure of my triangle here, and since I know what the opposite side is 30 here, and I know the hypotenuse here is 60, I can use the inverse sine to find out the angle here. So the inverse sine of the opposite over the hypotenuse is 30 degrees. Since the sine of opposite over hypotenuse is equal to, sine of theta is equal to the opposite over hypotenuse, the inverse sine of the opposite over hypotenuse is equal to the angle theta. I could have really used any of the, since I know all three sides, I could have used the inverse tangent. If I would have used opposite over adjacent, that's what we're used to, you would end up with the same number, no matter which trig function you used, as long as you chose the right sides to use. Anyway, we get 30 degrees from that right triangle's structure, and so I'm going to use that now as I'm calculating these components. So the horizontal component is F2, 0.005 newtons, times the cosine of negative 30 degrees, and I get the 0.00433 newtons. And the vertical component, likewise, the 0.005 newtons times the sine of negative 30 degrees to get the vertical component. So we're going to go to the next slide now, taking these components that we have and finding out what the resultant vector is going to be right here. All right, so now with a little more white space to work with here, a little more room, let's go ahead and find the total components here. So the sum of all the horizontal components, again, there was in F1 right here, there was no horizontal component. And then the horizontal component of force 2 was the 0.00433 newtons. And I'm keeping a few extra significant digits here just until I get to my final result. So that's our horizontal component. And notice that it's all due to F2 here. It would be that much right there. And then the vertical component, notice that the F2 is pointing downward, so it's going to eat away a little bit at F1 right here. That's why when we take the diagonal here, that's going to be the resultant force. So anyway, the vertical components, adding those two together, the 0.02 newtons here minus the 0.0025 newtons right there will give us the vertical component. Now I have my two components. I can use the Pythagorean theorem here to find the hypotenuse, and doing that, I didn't draw the square root. I did negative to the -2 is the same thing as the square root here. But anyway, the resultant force is going to be equal to the square root of the horizontal component squared plus the vertical component squared. And so doing that here and here, we get 0.018 newtons. And again, that is going to be right about in here. And now we have to find the angle. And that angle is referenced to this horizontal line right here. So it's really going to be an angle up to wherever that vector is. So our angle here is the inverse tangent of our vertical component over our horizontal component. And so doing that, we get 76.1 degrees. And here's what that looks like. If I take F2 and pull it off and put the tail of it on the tip of F1, it should come down to about right here. And when I do that, this is the resultant force. And we should feel pretty good about that because a 0.018 is a little bit smaller than the 0.02. So if I rotated this back up to about right here, you can see that that's about right, about 0.018 long. And then you can also see that this angle right here makes sense that it's around 76 degrees. That's 90 degrees to there. It's a little less than that, and so that looks proper as well. So now that we've found the force vectors here, let's go ahead and find the electric field vectors at Q3. Okay, notice that the electric field, since we have Q3 as a positive charge, like a positive test charge, that the electric field vectors would be in the same direction as the force vectors. The only difference is that they would be scaled a little bit differently here, because the electric field is just KQ over the distance. And so understanding that, to find the electric field here due to Q1, we just have to take F1 and divide by Q3, the test charge. And doing that, we would get 5 times 10 to the 6 newtons per coulomb. Notice that those are pretty big numbers always for the electric field strength. And likewise, the electric field here associated with Q2 would just be the electric force from Q2 divided by the test charge Q3 amount, and so that would be 1.25 times 10 to the 6 newtons per coulomb. And then the total electric field between these two, we could take the total force and divide by the test charge amount here and get our 4.5 times 10 to the 6 newtons per coulomb. So that's how we could find the electric field strength. And again, the vectors would all be pointing same direction and have the same relative sizing and so forth. It's just that they'd be different numbers in these places. So potential is our next challenge. And down here we're looking at the different potentials. Notice that potential is, we have these force vectors or electric field vectors, but potential is a scalar. It's not a vector. So V1 is would just be KQ over R. So since it's just KQ over R, we could, if we know the electric field strength, we can just multiply by the distance R to scale it to 1.5 times 10 to the 6 volts. You could also have found V1 by taking K, the 9 times 10 to the 9th, and multiplying it by the 50 microcoulombs and then dividing it by the 0.3 meters. You would get the same answer. Likewise, V2, the easy way when I know the electric field strength is just to multiply by the distance here. And doing that, I can get the voltage or the potential at Q3 relative to Q2 here. Again, I could have taken KQ over R2, where Q is the negative 50 microcoulombs, and gotten the same answer. Potential is just adding the two different potentials together. This is a negative potential because it comes from a negative charge, and so when we add those two together, we get the overall potential here at this location relative to those two charges. Notice that Q3 does not play a role in this. We're just finding a location in space and seeing how these two charges would create their own potentials, adding these two together. And that's it for potential. Let's use PhET to check out our problem here. This is our positive 50 microcoulomb charge, and I'm going to put Q3 30 centimeters away, and there's our force vector, or also the direction of the electric field vector associated with Q1 at this location Q3. Next, I'm going to clear, and we'll see what the negative charge does. And so here's our negative charge, 52 centimeters away relative to Q3, and that's the force vector F2 or the electric field vector F2. So now let's put it all together. And here we go. That's our overall net force vector with the summation of our two forces F1 and F2, or the electric field vector would point in that same direction. And questions to answer. How do you calculate electric force, field, and potential with three charges? And what do the force and electric field vectors look like when added together? Scratch's parting idea. And good luck striving for continuous improvement.